Welcome to BOSFest 2021. I am Anwesha Chakraborty and will be presenting my talk on forced harmonic oscillator in non-commutative spacetime and emergence of geometric phase. The aim of this project is to study the effect of spacetime non-commutativity on dynamics of time-dependent quantum system. Literature study shows that the dynamics of a time-independent system is unaffected by the non-commutativity of spacetime and only the wave function gets modified. So it is intuitive to study a time-dependent system placed in a non-commutative spacetime, and for that we have used a forced harmonic oscillator as our toy model, as it also has many applications in quantum optics and physics. We have shown that a geometrical phase shift is emergent in the above system when placed in a non-commutative or quantum spacetime. Now I will briefly outline the plan of my talk. First, I will start with time reparameterization invariant form of action, then show the quantum spacetime arising from a classical toy model, and then formulate the quantum mechanics of quantum spacetime or non-commutative spacetime. Then we will place a forced harmonic oscillator in such spacetime and see its adiabatic evolution and emergence of Berry phase or geometric phase. Now then we will conclude with some comments. To do the quantum mechanics on non-commutative spacetime, the first challenge is to promote time at the level of operator along with the space coordinates. So we start from a reparameterization invariant toy model for non-relativistic system, and for that we will treat time as a configuration space variable at par with the position, and we will take a new parameter tau as an evolution parameter and parameterize time as function of tau, and we take it to be a monotonically increasing function of tau. And so t dot is given by dt d tau and x dot is given by this expression. A non-relativistic Lagrangian in this case, which is generally dependent on position and its generalized velocity, will now depend on time, position and their corresponding generalized velocities and tau, the evolution parameter. So let us take a simple example of a non-relativistic system. It is the kinetic and it is the potential term. Now in terms of the evolution parameter tau, the Lagrangian takes the following form in equation 1, and the corresponding canonical momentas Px and Pt are given by equation 2. We see that the second term in second equation in 2 is a constant equation, and it is a primary constant of the system, as Pt is not dependent on the generalized velocity corresponding to t. So phi is a constant of the system, and the total Hamiltonian of the system can be written as this, where sigma is a Lagrangian multiplier. Now, the first order form of the Lagrangian can be written by a Legendre transformation of the Hamiltonian. In first order form, momenta variable and configuration space variable both are taken as configurations variable, and we have an enlarged configuration space variable. Now, we can run the constraint analysis process and compute the Dirac bracket to get the bracket 6. We see that the Heisenberg algebra arises naturally from this kind of system in the Dirac bracket level. So now again the system is still left with a first class constant phi, which is basically the generator of the gauge transformation and is responsible for the tau evolution. We can now quantize the system and take the operators, elevate the t and x to the level of operators and get the usual Heisenberg algebra, and finally the time dependent Schrodinger equation is obtained by demanding that physical states psi to be gauge invariant, or in other words, the first class constant annihilates the physical state of the system, and we will get the usual Schrodinger equation. Now we take a second example where we append the previous Lagrangian, first order Lagrangian, with this kind of term where it is a Chern-Simons like term in the momentum space, and theta being the coupling constant. Again, if we run the constant analysis and compute the Dirac brackets, we will land up with the brackets in equation 10, and we will see that the configuration space variable itself gives a non-zero Dirac bracket. We can now elevate it to the level of operator to get a non-commutative Heisenberg algebra, as in equation 11. We can see that time and space no longer commutes with each other, and theta, which was the coupling constant in this form, is a non-commutative parameter. Now, to represent the space-time algebra, we find the Hilbert space HC, which furnishes the representation of this coordinate algebra, and HQ is another Hilbert space, which is a unitary representation of the entire non-commutative Heisenberg algebra, which is basically the elements of this is basically the algebra of polynomials generated by T and X operator, and these correspond to the compact trace class operator. And the action of phase space operators on any element of the space HQ psi is given by equation 14. We see that capital T and capital X is used in place of small t and small x respectively to distinguish their domain of action respectively in HQ and HC. Now, again, the Schrodinger equation or constant equation still holds in this case in presence of non-commutativity, and we would like to construct an explicit space-time coordinate representation of the above operatorial version of the Schrodinger equation. And as mentioned earlier, as we have seen earlier, that there does not exist any common eigenstate of T and X operator. So we need to find a coherent state basis, which is Z bar living in the space HQ, and we can get the space-time representation of a arbitrary psi like this, taking its coherent state representation. And likewise, we can take the coherent state representation of the Schrodinger equation and get an effective commutative theory. So we will now go to our system, which is a forced harmonic oscillator system. So if we now quantize the space time with where non-commutative space-time is capital T and capital X, the Hamiltonian takes the form. Here this extra time arises because of the operator of ordering. And we take the coherent state representation of the Schrodinger equation to get the equation 21, where px, x theta and t theta are the coordinate representation of the space operator in coherent state basis. So finally we get a effective commutative description where the commutative Hamiltonian is given by equation 23, where the first three terms represent the Hamiltonian of a generalized harmonic oscillator, time dependent, and these are the linear term in x and p. We can see that alpha and gamma are derived variables and depends on time, and we consider R to be consisting of alpha, beta and gamma to be a time dependent parameter space which varies periodically with time period capital T, and the system Hamiltonian thus changes adiabatically through these parameters so that they can make a circuit in the parameter space, and the Hamiltonian comes back to its initial value, and as a result over and above the usual dynamical phase, it gives rise to a Betti phase. And the main culprit to give rise to Gary phase is this term, the dilatation term. We'll come back to this later. So in Heisenberg picture, if we calculate the equation of motion for the ladder operators, we see that first I want to tell that here xi and x are the contains the first and higher order derivative of the parameters alpha and gamma. As we have already told that alpha and gamma are adiabatic parameters, so we will only consider and keep the first order time derivative of alpha and gamma and throw away the second and higher order time derivatives, as it varies very slowly with time. So we obtain the behavior of adiabatic transferred around a closed circuit accomplished by a total time period of t and get this equation 27. So the first one is the dynamical part, and the second one is an extra phase factor over and above the dynamical phase, because when we write the time derivative in terms of the gradient operator in the parameter space like this in equation 28, we can see that the second phase factor can be written as a line integral in the parameter space over a closed circuit gamma. This is the usual form of the Betti phase, and we can again apply a Stokes theorem relating the line integral over a closed curve in the parameter space to the surface integral with its boundary gamma. We can see the phase factor takes a form like equation 29. And if we write this equation in terms of the original parameters, we see that it explicitly depends on theta and goes to 0 if we put theta to be 0. So now we will comment on the findings that when a forced harmonic oscillator is placed in a non-commutative space-time, a dilatation like term occurs as a commutative description, and this is the main culprit to give rise to the Berry phase. As we can see that gamma depends on theta, and if we switch off the non-commutativity, theta goes to 0 and this term vanishes and the Berry phase also vanishes. And also in this reference it is already proved that if a Hamiltonian of a system can be written in terms of Lie group generators, then like SU11 and SU2 specifically, the occurrence of geometrical phase is a natural consequence. As we can see that our Hamiltonian can also be written in terms of the generators of a SU11 Lie algebra, x square, px square, and symmetry combination of x and p. So the occurrence of geometric phase is a natural consequence here. Thank you everyone, and I would like to conclude my talk here.